So, hash tables. All right. Now, if we look at this, the Wikipedia page is in computing a hash table. A hash map is a data structure that implements an associative array abstract data type, a structure that can map keys to. That's a bunch of gibberish, right? If you read, basically the issue with hash tables is honestly, I think they're pretty hard to teach. So first off, what is the hash table? The hash table is the underlying data structure we're going to use to build a map or an associative array or a dictionary or whatever you want to call it. And the idea here is that we need on average constant time. Basically, pretty much every call we do, we want to be able to say it's constant time. We want to be able to access any entry directly through its key value rather than having to search for it. In other words, given a key, I want to know the value associated with it instantly. And as far as we know, there's only one thing we can do to do that, which is an array, right? Given the key of an index, right? Given the key of an index, I can get the associated value with that key with that index in constant time, right? If you remember back to when we were going over array lists, the big thing about array lists is that you could get and set at a specific index in constant time. That's basically so. So in other words, pretty much everything we're going to rely on needs to use an array, specifically the get and set operation for an array. All right. So in that case, we've got three challenges here that it's kind of just a whack-a-mole problem where basically each of the challenges that we propose and then come up with a solution for brings up some other ones. So they're all interrelated. But I like to put them in like three distinct points. The first problem we have is basically first problem, second problem, and then third problem. So what's one problem that we might have? One problem is we don't want just indices, right? We want keys. We want that generic key. In other words, if I give you anything, a word or something else, I need to be able to use that as an index, right? If I want to store the key cow and the value moo, if I ask for cow, the table should go moo, right? So problem one, need to store problem one, need to store any key not just integers, right? Not even numbers, right? We also want double to be a key as well. So any key, not just integers. All right. That one seems a bit hard, but actually it's kind of trivial to how to solve that problem. Okay? Because what is basically a string? What is a string? It's an array of characters. What are characters? Characters are what? What kind of are they're a specific kind of value, right? They're integers. Characters are integers. Basically, think about that for a second. I don't know if you learned about the IEEE floating point notation, right? How are doubles stored? How is everything stored? It's stored in some binary format. This means at its core, there is some way to always transform something into a number, right? Even if it's just taking the binary representation of it, right? So problem one is solved by basically pushing it off to some other problem. So problem two is we need to transform actually the solution to this is actually problem kind of, So, I mean, the problems here, we're just going to knock them off and then just come up with new ones. So we need to transform any key into an integer. Okay? So, worst case scenario, and the idea here is that basically we need to give it but not only that, every key kind of has to have a unique integer, right? So I could easily come up with a function that transforms any key into an integer right now. Okay, let's call it a function h. Given key k, right? There we go. I am done. Right. Every key has a unique, and every key goes to a integer now. Right? Just goes to the key 0, which is kind of useless here. So obviously we'll have to come back to that kind of idea. So we need to transform any key into an integer. Right? We're gonna these problems we're gonna come up with, and then we're gonna refine them further. Okay. And the other thing is that we need to use an array. Specifically, we need a big one. Why? Well, because we want to store anything we can in this, right? We want to do random key value associations. Let's just go back to integers for a second, right? I want to be able to say I need to store the I want to be able to store like the association one apple and 1 million pear. Okay, those are two keys I want to store. So naive solution, create a giant array, right? Create a huge array, right? And basically, so let's just like think about this for a second. Create a huge array. Essentially, the idea is that I'll take given a key, I'll turn it into an integer. That integer will be the index in this infinite size array, okay? And then we can do that. So that's kind of the idea here. Okay, let me go by that again. So given a I actually need the whiteboard for this. So the idea here is that we are going, the way we're going to solve this problem is that we are going to, given some key, I'm going to transform it into some integer, specifically an index, okay? I'm going to transform it into an index. And this index will go into this will go into a specific spot in the array. So basically, I'll have this really giant array here. So if I get the key 1, it will get transformed into the index 1, right? And then I'll store whatever value in index 1. If I give them the key 1 million, I'll store the value associated with 1 million in index 1 million, right? If I'm given the key apple, I'll maybe transform apple into the key 32,000, right? I'll transform it somehow. I don't know what the function I'm going to do to transform it, but I'm going to transform it, the key, into it, right? Whatever it is, into a number. Integers don't need to be transformed at all, right? Given an integer, just spit out that integer. And I'll store it in this infinitely sized array. Anybody see a problem with the infinite sized array, though? It's kind of in the name, right? It's a trick question. It's an infinite sized array. So first off, we've got, now let's assume I do have an infinite amount of array. We are dealing with Java over here, so how many values can I store in an array in Java? Sorry? So what's used as the index in an array? Integers. So what's the biggest integer? Ish. About 2 billion, right? A bit more than 2 billion. So that means that the biggest array is not actually infinite. It's about 2 billion. So, okay, that's a bit of an issue. Well, okay, but even that, okay, let's just say I make it as big as possible and store 2 billion values and leave the whole idea. So we now have two issues. The first is that basically we need to, so the issues are basically is that I've got this array, it's no longer infinitely sized, it's only 2 billion because that's the maximum things we can store, right? Okay. Okay, even if it's only 2 billion things, that's still 2 gigabytes of data that I'm using basically for every single program that uses a map. That seems a bit much of a sacrifice to get constant time lookup. And even in that case, transforming a key to an index, right? That needs to be a unique index. So let's rewrite this into a unique index. So we need to transform a key into a unique index. Okay? So the second thing is that we need an array, a big one, right? So we need an array. So the way we solve that is by, if we don't want a big array, the way to solve that is to make a small array, right? How big does our array need to be? Well, what we can do is that we can just make our array grow as we need. So how do we deal with like 1 and 1 billion? So let's say we've got this key and we've got this index over here. Yeah, let's say when we shrink down this table, made it a size 10. Okay? That means I can store 10 unique keys in this. Okay, so it's now size 10. I can store 10 unique keys. Okay, into this thing. How do I say? Well, how can I work this out? Well, what I could do is I could mod the index by 10, right? So basically, that would give basically everybody kind of a slot to go on. So if I stored in 1, it would go into 1 slot, and then if I were to store in 1 million, index 1 million, that would be I'd store that value in index 1 million mod 10. So what we do is essentially this process. Give it a key. I'm going to transform it using the hash function, something magical called the hash function. So solution number 1, you need to store any key, not just integers. Solution hash function. Turn it, in other words, give me a function, and that's a special function that will. So solution for 1 and 2 is actually the hash function, which simply says, given a key, I'm going to try to transform something into a kind of a unique integer. So solutions for 1 and 2 is hash function. And if we want to use a small array, what we'll do is that we'll do the following. We'll do an index, and then we'll mod it by the size of the table. And then we'll store it in the table. So it's all I'm saying here is that we've just got we have a bunch of hacks going on here, right? So problem 1 is so this first problem is transforming it into a unique index. Okay? So we've got a unique index. So what we do is that we give it a key, so maybe we give it 5 we give it like apple, and that gets transformed into like 32,001. Then we mod it by the table, so we use the hash function to figure out that apple's value is 2,000 is this 32,000 value. That gives us an index, but how do we store that index on a smaller table? We mod it by the table size. Okay. Now we're left with only one problem. What's the problem? So actually the first problem is solved by a hash function. The second one is this unique issue, which is that sometimes, so there's no real guarantee that you can give me that basically one key, that we've got an infinite number of keys, right? There's a literal infinite number of keys we can use. Like there's the entire English language plus every other language out there plus every single integer out there. And if you can't think of one, I'll give you another one just by adding one to the one you were thinking of. So, basically any possible key needs to be able to use. So it's possible. So we're putting an infinite possible number of keys in a smaller space, essentially, space that's not infinite, which means that basically we're going to have collisions. Has anybody taken Prob Stat here and learned about the pigeonhole principle? It's the stupidest proof ever, which is basically if you've got a bunch of pigeons, right, and you've got a bunch of pigeonholes, if you've got more pigeons than pigeonholes, that means then there's going to be a pigeonhole that shares 2 pigeons. That's the pigeonhole principle. That means that what we deal with is that there's something called collisions. So 2 is handle collisions. So problem 2 is basic. So problem 1 is transform need to store any key. You transform anything into a unique index. That's why unique is in quote. And then we need to deal with conflicts. Okay, and then we need an array. We can't use an infinitely sized one. So we use a small array. Smaller array. Resize as needed. Okay, use a small array, resize as needed, mod by size. And those are the ingredients to building a hash table. Now, there's 2 ways we can deal with these collisions. The first way is called open addressing, and the second way is called chaining, which sound super intimidating, but I'll summarize them in really easy to understand things, which is basically if my spot is already occupied, I'm just going to go and find the next available spot and I'm going to steal it. That's open addressing in a nutshell. That's how I deal with. That's one way I deal with conflicts. The other way I can deal with conflicts is that that the array I have is actually an array of linked lists. This is called hash table of chaining. So if I've got a collision, I just go into the end of the linked list there. And so basically to find something, I just iterate through the linked list. And then I prove mathematically that those linked lists aren't actually that big at all. So it's actually all just constant time. Really, I promise. Sound complicated? It can be. But it's actually, again, a very simple process for a hash table. Okay? The idea is that we use something called hashing. We use this index calculation. We get a key, we turn it into an index, and once we have that index, we can do constant time. Now, why does this work? Well, say you want to find the key associated with Apple. You just transform it into a number, and then you instantly find the index it's stored at. Right? There's no searching involved because all you're doing is a mathematical transformation. So how does a hash function work? Black magic. Black, arcane, deepest magic, because coming up with hash functions are serious business, and they're used for more than just hash tables. Anybody here of SHA-256? If you've been looking at Bitcoin, you know about SHA, the secure hashing algorithm. Same kind of thing. The idea is just basically given a file name, given a key, any kind of key, create some kind of unique 256-bit number. So it's very similar. The idea here of hashing is more than just hash tables, but it's very powerful. One of the common things that's used for is how many of you have seen MD5 or something like that? Okay, let's go ahead and let me go to Ubuntu.com. Okay, actually I'll go to Linux Mint because actually that's even a better example. Linux Mint is a very noob-friendly distribution of Linux, right? So what I want to do, and so Linux is an operating system. It's free. I could download it, right? So all I have to do to download it is I click on the link, click on a download mirror. Don't forget to verify your ISO. So I'll click over here and I'll download the ISO image. Don't forget to verify your ISO. You pretty much will skip over that. Almost everybody does. How do I verify that? SHA-256.txt checksum contains checksums for this. What the heck is these? Well, these are SHA-256 numbers. The idea here is basically that Linux Mint had an unfortunate incident a number of years ago when I was going for my PhD studies, which was that some malicious hacker managed to upload a compromised version of an ISO onto their servers. Basically, the idea here is suppose you're a government who knows that basically that a lot of developers use this particular distribution in a country that you want to surveil. Okay, say your country is your country A and you want to surveil country B, and you know that the developers of country B, they all like to use let's say Linux Mint. Okay, so say I'm like in the spy agency there, and I'm like, if I can break into their servers, not too hard because I've got a bunch of nice technical hacking tools that somebody else has developed that are classified, right? I could upload a compromised ISO image, right, in a compromised version of the operating system with a bit of software that will, the term is phone home. In other words, transmit me data of what they're working on. So let's say it will transmit, it's a script that runs whenever they run it. It's a hidden script that basically it searches their library, their disk for Java files or Python files or whatever files that I know that programs that they're working on, and then it emails to me. And now I've got all the proprietary information I'm spying on, and if I'm lucky, I've just found something that basically somebody who's working for B's spy agency is working on, which gives me their hacking tools. That's great. So. Okay, and this has not been just like a fear since the whole like cyber warfare things really started up. This has been like a legitimate fear of basically programmers since we started putting stuff on the internet. So the way we that you do deal with that is these checksums, or these well, not checksums, but these hashing algorithms. And the idea here is that you run this file, which is, remember, just a giant number. It's a big file, through this hashing algorithm, and it prints out a 256-bit number that is pretty unique. Now, this is a number. It is, I believe, hexadecimal. Yep, it looks like a hexadecimal number. So these are 16-bit. These are base 16 numbers over here. But basically, the way you can verify that your file has not been tampered with is by verifying it. By verifying this number, right? That the number you ran this CIS on this file that you downloaded matches this number. Now, mind you, of course, if you're properly paranoid, you may have figured out a problem with this, which is that if somebody hacks this website as well and puts also that compromised number up, right? Because the number should be, the way these numbers are generated is that making a slight tweak to any binary digit, any hexadecimal digit in the input should produce a radically different output. Okay, so the idea is that basically it's hard to create two files that look the same, that have the same key. It's possible, but that gets into PhD level research and master's level research at that. So I'm going to avoid that. But basically, the idea here is that by using this hashing algorithm, I can reasonably check that basically this file is the one I said that got downloaded. Okay. So hashing has like security implications too, but the hashing algorithms that we use here are slightly different here. So, in most keys are going to be a string of numbers, of letters or digits, right? You're going to be, so what you're going to do to generate. So let's just talk about how we, this is the algorithm we use. Given a key, we use the hash function to generate some kind of number, which we'll use as an index. Okay, that's the problem we'll try to solve right now. So a key is typically like this string of digits, right? It's either going to be like the username or an email address, or it's going to be some digits like a social security number. Rather, it's not going to be a single character. It's going to be or a number or like an integer typically. It's going to be some kind of unique number. So the idea here is that how do we generate an algorithm that basically can kind of evenly distribute it, so that given a number, right? So given a table, basically all the values that I store on the table get evenly distributed. So I reduce the number of collisions. And the idea is basically, and honestly, that's hard. That's hard. It's beyond the purview. Generating good hash algorithms is kind of beyond the purview of this class. It generally, the most simple ones deal with nasty bits of prime numbers and stuff. But let's look at how, and Java, and we know that's hard. So fortunately for you, Java has that all figured out for you. Okay? So now any object can be used as a key, right? That's what Java's promising. Any object can be used as a key. So that actually gives us an advantage in Java, which is that if I created like an object O, equal to a new object. Remember, you can do that. Let's look at the functions they have. Equals hash code. Oh, could that possibly be related to like our hash table things? I don't know why it's not coming up the documentation. Maybe I have to do this first. Yeah, documentation. Returns a hash code value for an object. This method is supported for the benefit of hash tables, such as those provided by java.util.hashmap. The general contract is, when it's invoked more than once, it will return the same integer all the time. When you use hash code, when you ask an object what its hash code is, you probably want to get the same answer back all the time. Otherwise, you're not going to be able to look it up, right? And the way it will work is that I think by default, what it does is that the hash code of the object is simply the memory location of that object. Not SQL outs. S out. So let's print out the object and let's print out its hash code. But the point being is that this is not a problem you have to solve. It is literally beyond the purview of this class. So it prints out object at D7B1517. And then it prints out a hash value for you. So it prints out a uniquely generated hash value using the memory location, I believe. How does it work for strings? You might think, okay, let's just turn all the integers and all the strings in, all the characters in the string into an integer, and then add those all together. But that would give you the same hash value for sign and sing. So the way it works is that it uses this complicated formula. Basically, it takes the first letter, multiplies it by 31 to the n-1, where n is the number of characters in the string, times s times 32 raised to the n-2, where n is the length of the string, and so on and so forth. Why 31? Because it's a prime number, and if you do the math behind these things, which I do not suggest at the moment because you've got enough on your plate right now, prime numbers really help reduce collisions. So for example, cat will have the hash code of c, which the value of c times 31 squared. Why 31 squared? Well, cat is 3 letters long, and is the first letter, so 2, plus a times 31 plus t. So all those values together give it a kind of relatively unique ID of 67,510. So it isn't going to be, strings aren't going to always return a unique string because there's a unique value because there's infinite number of strings, right? But it's fairly random. It's a fairly random value. So step one, so that first process of basically how do I store something, store a key, how do I take a random thing? So problem one, how do I store any key, not just integers? I'll use a hash function. Specifically use .hashcode. The second problem, I need to transform any key into a unique index, but that's going to deal, any key I get is not going to necessarily be unique. In other words, I'm going to have conflicts sometimes. Two things might have the same unique index, the same unique generated number. That's an issue. In that case, I have to do something called, I have to deal with collisions. And I said, we'll use either open addressing or, so the solution here is solution, open addressing, or chaining. And 3, we want to use the array, and we don't want it to be infinitely sized, so that's a problem. So instead we mod the table by the size. Okay. Yes.
So in other languages, when they say an object is hashable, do they mean like they have a...
That means that you can use it as the key for a hash table. When something is hashable.
You can't.
Sorry?
If they're not, you can't. It's not like Java.
Java, yeah, because everything is an object in Java, and every object has a hash code function. You can use any object you want for it. So hash functions should be relatively simple and they're efficient to compute. You want basically doesn't matter how big the file is. You want to be able to pretty much hash it quickly. So so now we need to figure out how we actually build the hash table. There's 2 ways to build it, which is open addressing and chaining. Okay, and in open addressing, we use something called linear probing, and honestly, this is just a bunch of big words that all mean. The way we handle this is that we look for if we have a conflict, we insert an item so we generate the hash code. We got an index. We mod it by the size. We get an integer. We mod it by the size of the table to get what index I need to be. And if I find that my space is already taken, what do I do? That's what a conflict is. What do I do? In that case, I just simply iterate through the array until I find an open spot, and I take the next open spot. That sounds like it shouldn't work, and it sounds like it leads to a highly unorganized clustering of data. You're exactly right. But this is, again, why we say that order does not matter for a hash table. And then the other thing we do is that we can do is something called linear probing. So let's see. Oh man, I see so many tired faces. And now, unfortunately, I cannot stop because I don't want to cut out a half an hour of class because that would put us very ferociously behind. But let me just mention, like, this might seem overwhelming because the next test is going to cover hash tables. What the heck do you have to remember for this, right? This is all complicated stuff. Honestly, what I'm more concerned right now about for hash tables is the how to use them. Now, the final exam, which I'm writing, and actually we have a meeting tomorrow, ostensibly, if we can get in, about writing the final exam, but I believe I'm the one who's volunteered to be responsible for that. The code for hash table, so hash tables aren't like ever like needed in any of the problems on the final exam. You don't need a hash table to or a map or a set to solve any of the problems on the final exam. But boy, do they sure make your life easier. And that's been the case for all the previous final exams. You don't need them, but they make your life easier. They make the code heck a lot more elegant. They make it a lot more efficient. And make it easy to write and easier to read. Always like seeing that stuff. Here, I'll probably give you one or two a problem on the next exam that basically says, here's a hash table. Here's the keys that I look for. Here's the values. Build it. Something like doing the most common string. Most common string is something like that. All right. So how do I build these things? Well, this is the way it works. So find an item in a hash table, whether to find it, to remove it, or to retrieve it, or to put it in. I compute the index that I would find that item on by using hash code and then the length of the table. If the value is null, that means it was never there, right? It's not there. If the item if the table is equal to the item, then the item's in the table. Otherwise, I continue searching by incrementing the index until either I find the item I'm looking for or until I hit a null entry. If I hit a null entry, if I find the item, I found the item. If I find a null, that means the item was never inserted in the first place. So it's essentially going to act like a circular array in that case. So here's a pretty good example of like how this works in practice. So let's say we've got Tom, Dick, Harry, Sam, and Pete, okay? And here's all their hash codes, right? This is the actual hash codes that should be generated by Java. And we're inserting them into an array of size 5, okay? Which means that basically the index they all want to get into is hash code mod 5. So Tom is 4, Dick is 4, Harry is 3, Sam is 4, Pete is 3. So Tom, we insert Tom in, we compute its hash code, mod it by 5, say insert that in index 4. Insert this one into, well, we would put it in index 4, but that's already taken. So open addressing says move on to the next possible space, which means we wrap around and put it in index 0. Harry maps to index 3. Sorry, their hash code is, Harry's hash code is this, right? And again, these are the keys. We don't care about the values right now. We're just simply saying this is where the value associated with Tom would go, where the value associated with Dick would go, where the value associated with Harry would go, where the value associated with Sam would go. Well, we'd try to go into this index because is everybody following why it's going into all these indices, right? Tries to go to index 4, tries to go into index 0, can't go there, so it goes into 1. And then, well, Pete tries to go everywhere, and then until it finds the empty spot. Now, as you imagine, this means that basically as the hash, right? So Tom and Harry, inserting those took constant time. It took one step. But because we kept having collisions, it required basically the amount of, as the amount of empty space went down, the amount of time it took went up dramatically, right? Think about it like trying to park a car in a parking garage, right? When you are parking a car in a parking garage and the parking garage is almost completely full, right? It takes forever to find that empty spot. Okay. On the other hand, if the parking garage is maybe half full, I mean, there's spaces pretty much everywhere. I mean, like, yeah, half the spaces are taken, but half the spaces are open, and you can just hop into them pretty quickly. So in those cases, it doesn't take too long. So it's kind of the same principle working on, trying to find the first available spot. If it's completely full, it takes a long time. So in this example, now look at if we're using a hash table that's much bigger. here we're using a hash table of size 11. Why 11? Because we're using prime numbers here to reduce the chances of collisions. So it's the same hash codes, but the modulus is different. Tom is at 3, Dick is at 5, Harry is at 10, Sam is at 5, Pete is at 7, right? So now they end up with completely different things. The only collision is between Dick and Sam. And that was only one collision, and it was pretty much immediately resolved. So the best way we reduce collisions is by having more space. That's why at the very beginning I said we are deliberately going to waste a whole lot of space to do this. We're going to waste a whole lot of space. We can and honestly, the best way to keep, and we'll see that the slides, they have like basically performance and they have a table. And basically, if we guarantee that, this is the average number of checks you have to do to insert something. If a hash table is 95% of the way full, it doesn't matter how big the hash table is, it's going to take 10 checks. Which even for a million items, that's not too bad. If it's half full, though, on average, you've got 1.5 checks. Let's call it 2 if we round up. 2 checks to insert a single item, which is a constant time kind of thing. So that's fantastic amount of time. So most hash tables, we're going to keep them either only 50% of the way full or 75% of the way full. And as soon as they fill up to 50% or 75% of the capacity, we are going to double the size of the hash table so that basically we can fit more items in it. Right? So we are going to basically waste a huge amount of space so that we can get this time dealt with. Okay. So so let's go ahead. So that kind of gets us the idea of how we build these things, right? So I will go ahead and start building one. Yes.
Why did you do modulus size?
Modulus size because the right we got a that's a great question because we have 11 is the size of the hash table here, right? So this is a hash code. This is a uniquely generated number for each of these things, and we need to find if we had an infinite size array, I could just simply put Tom in this space, and Dick in this space, and Harry in this space, and Sam in index 82,879, and Pete in index 2,484,038. Unfortunately, I'm a bit pressed for space. You might be working with something that has only a couple, your application might have only room for a couple megabytes to run. So you don't have the room to do an array of size of a couple billion to store all these possible things. So instead we make a much smaller hash table and then mod by the size of that hash table so that it gets in. Because if you mod by 11, we'll get a value between 0 and 10, which is a valid index to store it in the array. Right? Modding by the size of the table gives you a valid index. Okay. So this is going to look a lot like creating a linked list in some ways. So let's go ahead and do a new hash evening new. So let's go ahead and make a hash table. Okay. So the hash table has 2 generics, right? It's going to have keys and values. Okay. And another thing I'm going to do to make my life a bit easier is that I'm going to kind of have a special node class. Okay. But it's going to make sense. I'm going to call it an entry. Okay. And it also takes a key and a value pair. But it's kind of going to act like a node. But it's very simple. Entries are just simply going to store a key and a value. So an entry is simply a key value pair. The reason I'll need this will become apparent later, but it makes it easier to construct things if I say it now. So basically my my array is going to be an array of entries. That make sense? So it's going to be an array of these key value pairs. So I'm going to store the key and the value together just so that basically it's easy to check when I'm going through. It makes building this thing a heck of a lot easier. So the hash table has the following. So let's figure out our private attributes first. It's been a while since we built something from scratch like this in class. So private, the first thing we would need is a table of entries. Right? So this is the hash table over here. private entry, and it's going to use keys and values as well. Oops, did I change? Yeah, I changed the locale to Japanese. Interesting. Okay, so private int size, right? What's the size of the table? Private, in other words, how many things I put into the table. Private int, so let's go with private double, private final double, private static final double, max capacity. In other words, how much filled up I'm going to allow this table to get. And I'm going to say I only want it to ever get 50% of the way filled up. Okay. Once it's above 50% of the way filled up, I'm going to resize the table so that it's only a quarter of the way filled up. Right? Because the more empty this table is, it's the more parking spots are available. So the quicker the people, the information I'm storing can get parked into the hash table. To overuse that metaphor. Okay, so we've got our capacity, we've got the table, we've got the size. That will do for right now. We'll revisit this if we need anything. So constructor, public hash table. That's not really going to take anything else other than set up a table equal to a new array of entries, and it's going to say, let's go with the default value of 11, right? Not 10, because we want to use prime numbers, essentially. We want to use prime numbers here because that will help reduce the chances of collisions. Okay, so new table of 11, and then its size is going to be 0 because of course it's going to start at 0. Okay, and it's empty currently. So let's go ahead and figure out, okay, how do I actually add something to this? Public v add, so public v put k, put in a key of type k and a value of type v, right? And we want to return the value we are inserting, I believe. Okay? So the first thing we need to do is calculate what index I would like to store it in. And this is going to take a lot of revision, or a couple of revisions to do this. So the first thing I need to do is calculate the index I would like to store this in. So we can push that off to a function because I'm going to be using this a whole lot. So let's say public v, let's call it, actually make it a private function. Private int k, get index of key. So this will get me the index that the key is stored at. Okay, so for right now that will be return return, and remember the first thing we need to do, how do I turn this into a number? Use the hash code function because all objects have that. Mod by the table size. And that's it. Table.length. Okay, so int index is equal to is equal to get index of the key. Okay, and I've just made it a function in case I need to turn it into something different. Okay. So now, what do I need to do? Well, if I want to put it into the hash table, what I do is I simply say table index. So there's table index is equal to a new entry that holds the key and value. Oh, right, we need a constructor for this, so insert a constructor that takes in both of these things, so automatically generate that, boom. Okay, so that was that. That was easy enough. Okay. The only issue here is that I haven't handled a few things. Well, first I've got to increment the size over here, size plus plus. The next thing I need to do is there's a couple of issues here. The first issue is wait, what if there's already a key that has that's claimed that index, right? What if that's already taken? And the other thing is, what if your table's already, what if we've gone above capacity, right? So that's kind of a issue that we'll have to figure out how to deal with. So those are two issues there. So if index equals null, so sorry, if so basically if the table is empty over here, this is perfectly valid to do, right? If there's no entry at this location in the table, we're more than free to claim it as our own, right? Else, if it's not empty, though, well, there's a couple of things going on here, okay? Well, in this case, we have a collision, okay? So we need to look, so according to open addressing, what we do is we look for the next possible spot. So so let's go ahead and say while table index is not equal to null, while the space is not equal to null, index plus plus, although remember this could give us an out of bounds exception. So it's actually, we can't really do index plus plus. We need to do index is equal to index plus 1 mod table.length, because that will enable us to wrap around the table, right? This will enable us to wrap around to index 0. And this will find a spot, and once we do this, we can find a spot with an empty spot for us. Of course, the issue with this is that it's still not completely correct. Because remember, what if we insert this into the table? What if this is the last complication this is basically the second last complication of this type we have. What if we've already inserted, what if we want to insert the thing into the table, but this is the second time we're inserting this key into there, right? Remember, we want to be able to overwrite the previous key value pairing, right? In this this. Remember, so basically, to go back to this over here, right? I had this dictionary over here, and if I do D3 is equal to goodbye, I need to be able to overwrite that. So that's something else we're going to have to do. So it is 7:52. I feel like this is a perfectly good stopping point for us here. So the next lecture so I'm still operating under the assumption that I'm not going to be here next week. That could possibly change. If I'm here next week, I will finish up this lecture. If I'm not here, you'll have videos finishing up this lecture, and you'll be doing the assignment that you'll need to learn. Well, it's going to be rather epic. Yes. No. Exam will be on the 5th and 6th.
And what's the time lab on?
The timed lab will be on like that tree question that I went over today, like how do you traverse through a tree, and then also on heaps, on like some of how to do heaps. Remember, heaps use arrays. But okay, so that's what that will go over. I'm gonna go ahead and start uploading this